Hello everyone. Today we're going to take you through topic number 5, compound inequalities. Here are the objectives for today's lesson. We're going to teach you how to find the intersection and union of two sets by understanding the difference between the words and or when solving compound inequalities. And then we'll model some of them in both regular inequalities and word problems. Compound inequalities are two inequalities joined by the words and or. The solution set of a compound inequality formed by the word and is the intersection of the solution set of the two inequalities. The symbol upside down U is used to represent the intersection. Note, the intersection of two sets A and B is the set of all elements contained to both sets. So the way I remember and is that if, for example, if when you were a kid, your mom said you could only go to the movies if you cleaned your room and you washed the dishes, that you had to do both. If you only did one, if you only cleaned your room and didn't wash the dishes, you were not going to go to the movies. If you went and washed the dishes but didn't clean your room, you also were not going to the movies. And means both have to happen. And is represented in the middle here. So when we have two sets, the and is the middle of the data set, the things that they have in common. The solution of a compound inequality formed by the word or is the union of the solution set of the two inequalities. The symbol U is used to represent union. Note, the union of the two sets A or B is the set of elements that belong to either of the sets. So again, in the example that I gave earlier, if you have to wash the dishes or clean your room to go to the movies, as long as you do one or both, you get to go to the movies. So if I wash the dishes but I don't clean my room, I'll go to the movies. If I clean my room and I don't wash the dishes, I still go to the movies. If I do both, I did at least one of them, so I would go to the movies. The only way I won't go to the movies is if I don't do any of them. One of the tricks that I've learned in the past to kind of remember the symbols is that the upside down U, if you put a line across from it, makes an A for and. So that's sort of how we remember the difference between and or symbolically. Let's take a look at some examples. So I've got three sets, A, B, and C, and they each contain different numbers. First, I want to find A and B. A and B. Meaning I need what is in both A and B to be the same. So I write out A here. I see it's 1, 2, 3, 4, 5. And for B, I see it's 2, 4, 6. We're looking for things that they have in common. What do they have in common in both sets? In this case, there's two things they have in common. They both have a 2, and they both have a 4. So the answer here would be 2 and 4. For my second problem, now we're looking for A or B. So again, they just have to contain at least one of them one time. So essentially we're going through and merging the two sets together. So when I look at this, I could see that in A I have 1, 2, 3, 4, and 5. And in B I have 2, 4, 6. Now I already have the 2 written. I have the 4 written. The only thing that's different here is I need to add the 6. So this is A or B. Each one of these numbers is contained at least once in the number set. Some of them are contained more than once, and that's okay. They just have to be contained at least once in the set of numbers. We continue with the same data sets. Now I want to find A and C. So again, I'm going to look at A and C, and I'm going to see what do they have in common. I look at the data sets. I don't see a -1 in both of them. I do see a 2 in both of them, so they have that in common. I see a 5 in both data sets, and I do not see an 8. So the only things that they have in common are 2 and 5. When I look at A or C, now we're trying to basically go through and merge the data sets. Anything that they have, I need to write at least once. So So in this case, again, I have 1, 2, 3, 4, 5 from A. And the only things that are different in C is that I have a -1 and an 8. This set contains at least one of everything that is in A or C. For my last set, I have A and B and C. So I want to go through and I want to figure out what do all the data sets have in common. Now if I look at data set A, I look at 1, but I see B doesn't have any 1s, so 1 will not work. I see all the data sets have a 2, so I can include 2 as part of my answer. I go to 3 and I see data set B doesn't have a 3, so we'll get rid of that. I go to 4 and I see that while B has a 4, C does not have a 4 in it, so I will get rid of that as a possible answer. And when I go to 5, I see that data set B doesn't have a 5 in it, so I will get rid of that. All these other values cannot be in all sets because we've got rid of all the values for A, so I can cross out the rest of these as they're not going to be in all the data sets. 2 is the only number that is in all 3 data sets. It's the only one that is in A and B and C. Let's continue here with this problem. In this case, A says x is a number so long as x is odd. B is the set x is a number so long as x is even. And C, we have specific numbers 0, 5, 10, 15, and 20. The first one is A and B. So what it's asking us here is we need to find something that is both even and odd. Well, that number doesn't exist because you're either an even number or an odd number. So in this case, this would be no solution. So again, you can get no solution if none of the numbers fit in the data set. For B, it's the opposite. It needs to be even or odd. Well, again, you're either an even number or an odd number. So in this case, we would say all solutions. Any number we pick would work. The final one, we've got A and C. So it needs to be even and it needs to be in the set of C. So it needs to be any of these numbers here. So we're basically going to go through and look for even numbers. In this case, we're going to assume 0 is an even number. So 0, 10, and 20 are the even numbers in set C. 5 and 15 are odd. So our answer here would be 0, 10, and 20. Now let's go through and solve and graph these. Again, remembering and means they need to be both happen. So we're essentially going to take each of these equations and solve them separately, and we're going to look for where do they go through and intersect. Let's take the first problem, and our goal is to get x by itself. So in order to get rid of the positive 4, I'm going to subtract 4 to the other side. And the first thing it tells me is that x has to be greater than -4. Let's take the second problem and let's solve it. This time it says 4 times x is greater than 0. To get rid of multiplication, I'm going to divide, and I'm going to get x is greater than 0. So I need to find all the solutions where x is both greater than -4 and greater than 0. Let's put both of these on a number line and see what happens. So if I wanted to graph x is greater than -4, and I'm going to do that at the top here, we would have a open dot at the -4, and we would graph all the values going this way. If I wanted to graph the other one, which I will do here in green, if I wanted to graph x is greater than 0, again I would have an open dot because I wouldn't include the values, and I would go to the right. So again, and is where they intersect. We're asking where do both of the graphs line up and have the same thing graphed. And there's only one place that it does it. So if we notice kind of over here to the left of -4, there's none of the graphs. Between -4 and 0, we only see one part of the graph. But starting at the open dot of 0 and going to the right is where both of the graphs happen to be. So this is what we would want to graph here in it, which makes sense. If a number is bigger than 0, sometimes it's bigger than -4. So when you think about it logically, if I picked, for example, -2, -2 would be bigger than -4, but it would not be bigger than 0. Whereas if I pick +2, 2 would be bigger than -4, and 2 would be bigger than 0. So the black part here is what I would use as my solution. In interval notation, we would have 0, and we don't include 0, so it gets a parenthesis, and it goes forever to the right, so it would get an infinity. So only the values between 0 and infinity, not including 0, would work for this problem. Or is the kind of the opposite. We're going to go through and solve it, and then as long as it exists one time, we're going to keep it in our solution. So again, we're going to solve each problem separately, graph them, and then we're going to see what we went through and graphed. Let's take the first problem. We're going to distribute the 5 into it. 5 times x is 5x. 5 times -1 is -5, which is greater than or equal to -5. I'm going to add both 5 to both sides. Now I've got 5x is greater than or equal to 0. And I need to divide to get x by itself. So the first part it tells me is that x has to be greater than or equal to 0. When I look at the second part, I've got 5 minus x is less than 11. I have to get rid of this +5. I'm going to do that by subtracting it to the other side. Over here I get 6, and this isn't x. Remember, this is -x. Remember, if we need to, if we don't see a number in front, we can pretend like there is an imaginary -1 there. My job is to get x by itself, so I need to divide both sides by -1. Remembering that if I divide by a negative, I need to flip the inequality sign. So the less than sign becomes a greater. 6 divided by -1 is -6. So for us, it says the solution is x has to be greater than 0, or x has to be greater than -6. Again, if we take a look at this on a number line, the first part is x has to be greater than or equal to 0. So this would be a closed dot at 0, and we would shade everything to the right. For the second part, it said x has to be greater than -6. It would be an open dot here because we wouldn't include -6. And then again, we would shade to the right. For an or, we keep anything that we graph. Anything that we graph is included on our number line. So essentially, we're not going to have anything before -6 because there wasn't a line here. Here I've got an open dot, and I'm going to shade all the way this way. And we can include 0 here, so we're going to keep going. And all the values that work are these. Anything from -6 on works. And again, it kind of makes sense if you think about it. If I choose -8 as an answer, -8 is not bigger than or equal to 0, and it's not bigger than -6, so it doesn't work. If I chose 4, 4 is both bigger than 0 and bigger than -6. And if I choose any number in between this, so let's say I chose -3. While -3 isn't bigger than 0, it is bigger than -6. And again, remember we had or, so it just needed to be bigger than one of them. So in this case, any of the numbers in here work. In interval notation, -6 is the smallest it can be, so it goes to the left, and it gets a parenthesis because of the open dot. We'll go to the right to infinity, which always gets a parenthesis. So again, or you can graph anything that is graphed. Let's try it again with this problem. So again, it's an or. We're going to keep anything that we go through and graph. 2x minus 5 is less than -3. My job is to get x by itself, so I'm going to add 5 to both sides. -2x is less than 2. I'll divide by a negative 2 to get x by itself. Again, I'm dividing by a negative, so I need to flip the sign. So the first part is that x has to be greater than negative 1. I have 6x is less than 0. For the second part, I'll divide by 6, and I get x has to be less than 0. So again, I'm going to go through and graph these, and notice what's going to happen when I graph these values. The first one says x has to be less than 0. So I could graph anything at 0 going to the left. This is x is less than 0. For x is greater than negative 1, I could go anything at negative 1 to the right. But if you notice this time, now my graph covers everything. So there's not a value that I can't pick that doesn't hold any of this true. For example, if I picked negative 2 is less than 0. If I picked positive 2 is greater than negative 1. And if I picked a number in here, for example, negative a half is both less than 0 and greater than negative 1. So this is an example where we would shade everything. And in this case, our answer would be all real solutions. Any number would work. And remember, in interval notation, we represent that as negative infinity and positive infinity. Now, I do want to point out, if this were an AND problem, we would only keep this middle part here, because this is the only part where they both shared. So as an AND, my answer would have been negative 1 to 0, and they both would have had parentheses because I couldn't include any values. So again, or we can keep anything that we shade, and we would have only kept the intersection. So please understand the difference between or and as we go and solve these problems. Here we have an in-between problem, and we saw this back in topic 4. This is really just going through and it's making it another compound inequality. Our job is to get x by itself in the middle. Now, you've probably learned before in math, whatever you do to one side of the problem, you do the other. We're basically going to do the exact same thing here, except we're going to say whatever we do to the middle, we're going to do the same to the outside. So our job is to get the middle to have x by itself, and then we're going to do the same to the outsides to get rid of it. So for example, I got 2 plus 2x here. I need to get rid of this positive 2, so I'm going to subtract the 2 from the middle. Whatever I do to the middle, I'm going to do the same to the outsides. Here these 2's will cancel. 4 minus 2 is 2. I still have the 2x here in the middle. 8 minus 2 is 6. My job is to get x by itself in the middle, so I need to divide by 2, which will leave me with just x. But whatever I do to the middle, I'm going to do the exact same to the outsides. 2 divided by 2 is 1, and 6 divided by 2 is 3. Now again, remember, this is really just saying x is between. So when I look at this, this is really telling me that x is between 1 and 3. So when I go to graph, I know that the values are going to be in between 1 and 3. They both can't equal them because they don't have the sign underneath it, so they both will be closed dots or parentheses, and then we will go through and graph in the middle of it. So again, all of these problems are compound inequality problems. These are basically AND problems, where it's saying x is between 1 and 3 in this case. We will do the same for this problem. Again, it's an AND problem, so we're going to go through and try to solve it. Let's distribute the 2 here to get rid of the parentheses. 2 times 1 is 2. 2 times negative x is negative 2x. I need to get rid of the positive 2, so I'm going to subtract 2 from both sides. I'm sorry, whatever I do to the inside, I'm going to do to the outside. So I have 2 less than negative 2x, less than or equal to 6. This time I'm going to divide by negative 2 to get x by itself. Whatever I do to the inside, I need to do to the outsides. Remembering again, the inequality signs are going to flip. So in this case, they all flip to greater than or equal to. And really, all that's going to do is just make sure that we graph it correctly. It still says x is between, but now it's x is between -3 and -1, because we always want the smaller number on the left. So as I go to graph it, here's -1, here's -3. -3 does have the equal sign on it, so we can include it, so it'll have a bracket. This will have a parenthesis, and then we'll shade in between as we do it. Interval notation wise, this would be -3 to -1, with the -3 getting the bracket. Again, this chart is we saw on topic video 4. Here's some keywords for solving word problems with inequalities. Again, if you need it, make sure you have it down. We can again go through and solve some of these compound problems with inequalities as we do this. Let's solve some word problems. You are having a catered event. You can spend at most $1,200. The setup fee is $250 plus $15 per person. Find the greatest number of people that can be invited and still stay within budget. So in this case, the unknown is the amount of people that we're going to invite. So we're going to call X people. It says that we have to spend at most $1,200, meaning we can spend up to $1,200, but we can't go over it. So that would be less than or equal to $1,200. The setup fee is $250, so we're going to pay that regardless of how many people we have. And then we're going to do $15 per person. Since we don't know how many people, we'll call that X. We're going to go through and solve this for X. So we're going to subtract 250 from both sides. 15x is less than or equal to 950. I'll divide both sides by 15. And I get x is less than or equal to 63.3. Now, you cannot have a fraction of a person, and we need to stay within budget. So it says as long as we invite 63.3 people or less, we will stay within budget. So the only amount we can invite is 63. We invite that 64th person, we are going to go over our budget. Finally, we have the formula for converting Fahrenheit temperatures to Celsius temperatures is C equals 5/9 times F minus 32. The average low temperature in Orlando was 24 degrees in July. The average high temperature was 33 degrees. We're going to use the compound inequality to convert these to temperatures in Fahrenheit degrees. So we are starting with our formula for Celsius. And we're saying that the average low was 24 and the high was 33. So we're going to put them on both sides. We're going to put the low number here, and we're going to put the high number here. And our job is basically to solve it for F, because if we do that, it'll then convert it to Fahrenheit and have the same temperature with it. So we're going to kind of unwind everything in the middle to get F by itself. The first thing we're going to do is get rid of this divided by 9 on the bottom. The opposite of dividing by 9 is to go through and multiply by 9. But whatever I do to the inside, I've got to do the same to the outside. As I do that, 9 times 24 gives me 216, which is less than or equal to, the 9 is gone. So now I have 5 F minus 32, which is less than or equal to 9 times 33, which is 295. My job is to get F by itself. It says F times this. We can distribute if we want, or we can just kind of divide here by 5, because it's saying 5 times the quantity F minus 32. So if we do that, we can kind of get rid of these 5s in one shot and just leave me with F minus 32 on the inside. But if I divide the middle by 5, I have to divide the outsides by 5 as well. 216 divided by 5 is 43.2. 295 divided by 5 is 59. Now I need to get rid of the negative 32, so I'm going to add 32 to both sides. When I do that, I have F by itself in the middle. 43.2 plus 32 is 75.2. And then I have 59 plus 32 is 91. So it's saying 24 degrees to 33 degrees is the average high temperature in Celsius, is the equivalent of the low in Fahrenheit being 75.2 degrees and the high being 91 degrees. But again, with compound inequalities like this, whatever you do to the middle, you're going to do the exact same to the outside.